There is no requirement in the National Electrical Code, also known as NEC, that specifies a minimum distance between a residential electrical distribution panel and a water source. This is crucial to understand the specific requirements outlined in the NEC to ensure safe and compliant electrical installations. Misinterpretations or local amendments to the NEC can sometimes lead to confusion, so it's always best to consult the latest edition of the NEC and local authorities for clarification. The NEC focuses on preventing electrical hazards and ensuring the safe operation of electrical systems. While it doesn't mandate a specific distance from water sources for residential panels, it does address the need for adequate working space and protection from physical damage. Section 110.26 of the NEC covers workspace about electrical equipment. It requires sufficient access and working space around electrical equipment to permit safe operation and maintenance. The depth of the working space depends on the nominal voltage to ground and the condition of the space opposite the equipment. Firstly, for equipment operating at 150 volts or less to ground, a minimum depth of 3 feet is generally required when there are exposed live parts on one side and no live or grounded parts on the other side of the working space, or where exposed live parts are on both sides but protected by insulating materials. Secondly, for equipment operating at voltages between 151 volts and 600 volts to ground, the required depth increases. If there are exposed live parts on one side and grounded parts on the other, the minimum depth is 3 feet. If there are exposed live parts on one side and insulated parts on the other, the minimum depth is also 3 feet. However, if there are exposed live parts on both sides of the working space, the minimum depth increases to 4 feet. Thirdly, for equipment operating at voltages between 601 volts and 1000 volts to ground, the minimum depth requirements are even greater. For exposed live parts on one side and grounded parts on the other, the depth is 4 feet. For exposed live parts on one side and insulated parts on the other, the depth is 4 feet. And for exposed live parts on both sides, the depth is 5 feet. The width of the working space must be at least 30 inches or the width of the equipment, whichever is greater. The height of the working space must be at least 6½ feet or the height of the equipment, whichever is greater. This clear space ensures that electricians have enough room to safely work on the electrical panel without obstruction. In addition to working space, the NEC addresses protection against physical damage in Section 110.27. Electrical equipment must be protected from physical damage that could compromise its integrity and safety. This could include protection from impact, abrasion, or other forms of mechanical stress. The NEC also addresses damp and wet locations in Sections 312.2 and 312.3. Enclosures for electrical equipment installed in damp or wet locations must be suitable for the environment. These enclosures are designed to prevent moisture from entering and damaging the equipment. Damp locations are areas subject to moderate degrees of moisture, such as some basements and barns. Wet locations are areas subject to saturation with water or other liquids, such as car washes and unprotected outdoor locations. While the NEC doesn't specify a minimum distance from water sources, it does require that electrical equipment be protected from water damage. This can be achieved by using enclosures rated for wet locations, as specified in NEC Section 314.15, or by installing the equipment in a location where it is not likely to be exposed to water. It's also important to ensure that any conduits or raceways entering the enclosure are properly sealed to prevent water from entering. The type of wiring method used can also play a role in preventing water damage. For example, using underground feeder or off cable, which is designed for direct burial, can provide additional protection in wet locations. Ground fault circuit interrupters, or GFCIs, are another important safety device that can help prevent electrical shocks in areas where water is present. GFCIs are designed to detect small imbalances in the electrical circuit, which can indicate a ground fault. When a ground fault is detected, the GFCI quickly trips the circuit, cutting off the flow of electricity and preventing a potentially fatal shock. The NEC requires GFCIs in many locations where there is a risk of exposure to water, such as bathrooms, kitchens, and outdoor areas. Specifically, Section 210.8 of the NEC outlines GFCI protection requirements for dwelling units. It mandates GFCI protection for 125 volt through 250 volt receptacles supplied by single-phase branch circuits rated 150 volts or less to ground in various locations, including bathrooms, garages, outdoors, crawl spaces, unfinished basements, kitchens, and laundry areas. Arc fault circuit interrupters, or SIs, are another type of circuit breaker that can help prevent electrical fires. SIs are designed to detect arc faults, which are dangerous electrical conditions that can cause fires. Arc faults can occur when electrical wiring becomes damaged or loose, creating a spark that can ignite nearby materials. SIs are required in many areas of the home, particularly in bedrooms and living areas, to provide protection against electrical fires. The NEC outlines of SI protection requirements in Section 210.12, specifying where SI protection is required for branch circuits supplying dwelling units. In addition to the NEC, local codes and regulations may have additional requirements for electrical installations. It's important to check with the local building department or electrical inspector to ensure that the installation complies with all applicable codes. Local codes may be more stringent than the NEC in some areas, particularly in areas prone to flooding or other water-related hazards. The size of the service for a residence is determined by the calculated load, following the procedures outlined in Article 220 of the NEC. This article provides methods for calculating branch circuit, feeder, and service loads. Factors such as the square footage of the dwelling, the number of appliances, and the heating and cooling systems are taken into account to determine the total load. Section 220.82 provides an optional method for calculating the service load for a dwelling unit. This method allows for a reduced load calculation compared to the standard method, provided certain conditions are met. These conditions typically involve the size of the dwelling, the heating and cooling equipment, and the appliance load. The 800 amp service mentioned is substantial and would typically be required for a very large home with extensive electrical demands such as multiple air conditioning systems, electric vehicle chargers, and other high load appliances. An 800 amp service requires careful planning and coordination to ensure that the service entrance equipment, conductors, and overcurrent protection devices are properly sized and installed. The main service disconnect must be readily accessible and located in a convenient location, typically near the point where the service conductors enter the building. The disconnect must be rated for the available fault current and must be able to interrupt the full load current of the service. The overcurrent protection for the service, such as a main circuit breaker or fuses, must be sized to protect the service conductors from overload in short circuit conditions. The size of the overcurrent protection device is based on the ampacity of the service conductors. The service conductors must be sized according to their ampacity, which is the maximum amount of current they can safely carry without overheating. The ampacity of conductors is determined by their size, insulation type, and installation conditions, as specified in NEC Table 310.16. It is also important to consider voltage drop when sizing service conductors, especially for long runs. Voltage drop can reduce the performance of electrical equipment and can even damage sensitive electronics. The NEC recommends limiting voltage drop to 3% on branch circuits and 5% on feeders and services. The grounding system is a critical component of the electrical system. It provides a path for fault current to return to the source, allowing the overcurrent protection device to trip and clear the fault. The grounding system must be properly installed and maintained to ensure its effectiveness. The grounding electrode system typically consists of a ground rod, a metal underground water pipe, or a concrete encased electrode, also known as a UFA ground. The grounding electrode conductor connects the grounding electrode system to the service equipment. The size of the grounding electrode conductor is based on the size of the service entrance conductors, as specified in NEC Table 250.66. Bonding is another important aspect of the grounding system. Bonding ensures that all metal parts of the electrical system, such as enclosures, conduits, and equipment grounding conductors, are electrically connected together. This creates a low impedance path for fault current, which helps to quickly clear faults and prevent electrical shocks. The main bonding jumper connects the grounded conductor to the equipment grounding conductors at the service equipment. The size of the main bonding jumper is based on the size of the service entrance conductors, as specified in NEC Table 250.28. Proper labeling of electrical panels is essential for safety and convenience. Each circuit breaker or fuse should be clearly labeled to indicate the loads it serves. This makes it easier to identify and troubleshoot problems and can prevent accidental disconnection of important circuits. Panel schedules should be updated whenever changes are made to the electrical system. The NEC requires that all electrical panels be properly labeled with the manufacturer's name, voltage, and ampacity rating. Electrical inspections are an important part of the building process. Inspections help to ensure that electrical installations comply with the NEC and local codes and that the work is performed safely and correctly. It's important to schedule inspections at the appropriate stages of the project, such as after the rough wiring is complete and before the drywall is installed. In summary, while the NEC doesn't require a specific distance between residential electrical distribution panels and water sources, it does emphasize the importance of protecting electrical equipment from water damage, providing adequate working space, and ensuring proper grounding and bonding. It is always best to consult the latest edition of the NEC and local authorities for specific requirements and clarification. Electrical work should only be performed by qualified and licensed electricians to ensure safety and compliance with all applicable codes and regulations. It is crucial to prioritize safety and follow best practices to prevent electrical hazards and ensure the reliable operation of electrical systems. Remember to always de-energize circuits before working on them and to use appropriate personal protective equipment, or PPE, such as insulated gloves and safety glasses. When in doubt, consult with a qualified electrician.